basically there were 80 deep graphs, so your identity represented over time. There's no problem with this. So you change the view of that so you couldn't use simple systems like binary systems. Then the kids would recognize that, okay, well, it's different from grammar from what they had heard before. We'll say they was the same grammar as they heard before. Then, as is traditional developmental psychology, sort of like I do anything you can do better, developmental psychology became that I can get younger kids to do anything you already did. So there's a reason came from where people to do that business so that you want to do the same thing. So that's how it's evolved, and I think they're basically right. And then I took the most popular model was how the paper and psycholinguistics for a long time with Jet Element simple recurrent network, which was the PET model with a set of nodes that that intro context node, and I gave it identity over time. A rose is a rose, a tulip is a tulip, and active a lily is a blank, and it was basically equivalent of speechless. So these PET models could not get these basic functions that you can get very easily. It's not you can't represent a function like this in a PET model. In fact, there's something called an autoassociator, which is like J1 in your PET network class, or your machine learning class, I guess. So you, in principle, what you do is you train one of these networks, and sorry, I'm not going to show it, but you train networks, let's say you represented your inputs are binary numbers, so you represent 12 by activating the two nodes that are in the lower left there, and the output is supposed to be the two nodes in the top left. So you train it on 12. You say 110, my input 110, 0 my output, and then you use some kind of error correction algorithm that looks at the difference between what output is actually generated and what your target output is, and adjust the weights in order to do that. Very standard approach to kernel distributed processing. Goes back to the notion of a perceptron, very old notion of perceptron. Then you do another example. You say, now you give it 14, and over time, you start to have the correct weight in order to do that. So 14 is 842 on the bottom, 842 on the top. You initially structure all of these nodes to be random, all the connections to be random. Over time, the connections that are not helping you get weaker, the ones that are get stronger, and eventually, when I feed in the same input, the model gets the right output. So if I train this kind of model on all the even numbers, now test it on odd numbers, it will systematically give us the wrong answer, no matter what your random weights are. It will systematically tell us that the one output node should remain as a 0, period. So you give it 15 as the input, and it tells you 14 as the output. You give it 3 as the input, and it tells you 2 as the output. So the systematic problem with these kinds of networks, one way to think about it is that each of the output nodes is an independent classifier. So the gate node sits there and anthropomorphized, which makes it easier to talk about. The gate node sits there and says, well, what are the circumstances that I should trigger? And it notices some examples over time. It says, I get it. Whenever the gate node input node is active, I will trigger it. Otherwise, none of this stuff is relevant. That's what it is that I mentioned. The 4 node, meanwhile, is doing a kind of parallel thing. And it says, well, when should I trigger? Well, when the 4 input node is active. The 1 node, meanwhile, this is the 1 node. This is where you can see if you're following. The logic, if you're following the logic, you should know that the 1 node is sitting there and says, I never turn on. Game over, there's nothing else for you to do. So the 1 node, because it's being tuned independently from the others, because it's always being told not to turn on, including it should not turn on, it's mathematically reasonable. It just doesn't capture the way humans think about these kinds of problems. And that's because humans think about them as operations of variables. They're looking for lawful things that they can be told classes rather than marginal problems with little things. And then you come to a case where people actually do something like this, like sensory motor coordinate transformations in these hospital cases. But we do language systems. Giving us some how that was all about in the 80s. Minsky and Tappert showed that kids had to usually couldn't even do exclusive OR, so people gave up. Most people gave up on the system. Even Minsky and Tappert realized that you had to use it to do something better, but they thought there was no systematic way to train the networks. And in the 80s, people found systematic, not perfect, but systematic ways to train networks that had to use this, and that's why it was so much excitement, because people knew that you had in unit, you could suddenly do nonlinear, separable functions, which is a whole lot broader about it than people do. Linear, separable functions. People got very excited. That's why PET became popular, but they don't help at all for the problem that I just described. Your output independence remains an issue no matter how many you can use, no matter how many layers you have. Deep learning is probably about having multiple layers. Now we have a way of training multiple layers, but it still has, I believe, I haven't tested it, but I'm pretty sure it has the same problem. So the way I think about this is in PET models, there's a training space. It's not that they can't generalize at all. This is why they got so popular, even though they were really very limited. It's because people knew that the issue with generalization, they didn't think about it precisely enough terms. They knew it was generalization, and they saw that PET models could generalize. So if I train the network on 8 and 4 and 2 independently, the model would be able to put 14 together, even though it hadn't seen it before. So people said, wow, these models can generalize. You thought you needed rules to generalize, but we can get generalization out of these models. What they didn't realize is the difference between what you might call interpolation and extrapolation. So if I use 8, 4, and 2, now I'm getting 14. 14 is a space of examples that you've seen before, and you can handle them. There's a limit. You not always able to do that, but you can often do that. And so as I give you more examples, you have a broader training space, you can generalize more. So in my identity example, there are others you can construct. There's always going to be something outside the space. So if I only give even numbers, there's going to be an odd number that's outside the space, but I'm going to be able to generalize to it. Or I can make a bigger number that you've ever seen before. My definition of my usual proof of identity, essentially, any model not going to be able to generalize to that. So hierarchies of feature detectors do an impressive job of speech recognition, not character recognition, where what you want to do is basically identify this belongs to this class, this belongs to another class. This is an example of this phoneme or this letter or this number. If you have a finite bounded set of classes and a broad enough training space, you don't need to start into variables. For those kinds of problems, it's a reasonable approach. I think you use a lot of variables, but the first order classification is a reasonable approach for those kinds of problems. But they're weak in inference when you need to go beyond the space of training examples. I'll figure out which one. In hindsight, the PET creates instantiate each of the errors that I described. The models were too simple. They lacked any structures. They didn't relearn everything from scratch. They were presented relatively uncritical because they were mathematical, and relatively like, so they kind of disrupt people's keywords. And they work well for low-end paying fruit because they could generalize the data space, but they didn't generalize outside the training space, so they never got there to language and inference. I expect the same will happen with deep learning. The failures of classification networks to extrapolate are specificated when I start going long tail problems, which you guys are probably pretty familiar with. What you're doing is, if you collect quotas data on pretty much any problem, you're going to get a distribution sort of like this, where there's a lot of quotas data for some common examples and relatively little data for your less common examples. The common examples are easy for many, many machine learning algorithms, and the rare examples are typically pretty hard. So, for example, you can download an app for your iPhone for the Latent database, and you can contribute to the machine learning of vision, and possibly to the unemployment of all as machines get better, and visual identification. If you want to serve that cause, you're welcome to do so. And what people do is they take a snapshot of something, let's say a book, whatever is lying around, and you draw a little outline of it, and you upload it to the database, and that's the database grows and grows and grows. And then someone more likely to go along and say, well, what are the properties of that database? And of course, what happens is most people take pictures of books because there are books sitting next to them. Most people don't take pictures of aardvarks because they don't have any aardvarks on them. That means that the system is good at recognizing books and cats and so forth, but they're not so good at recognizing other things. Watson isn't going to use this. Watson does a lot of machine learning, but not a particular kind of record, that's not so much of it. For Watson, they decided from the start, basically what they were going to do, I have a quote from the technical paper, is they were going to use what was available on the web. And what's available on the web has a long tail issue. And that was fine. This is the secret I promised to reveal about why Watson works. 94.7% of the Jeffrey questions, which are the answers to Jeffrey, are titles of Wikipedia pages. So Watson works as well as it does because it's a very good information retrieval system. But Watson is not pushed towards genuine intelligence, if I can say that, because he doesn't have to deal with things that aren't titles of Wikipedia pages. So it doesn't have to confront the long tail problem. Watson is sitting in the sweet spot of the long tail distribution, which is fitting the fat left-hand part, and that's why it was able to work as well as it doesn't work at 100%. There's also some issues about how fast it has buzzers that humans will complain about. Even putting all that aside, the real issue with Watson is it can't do the kinds of things that people are trying to do here. It can't, for example, understand textbook because it doesn't have inferential abilities. So it's sort of literally written on the page, you can retrieve it when you need to go beyond it. Watson generally hard to press different steps here, which is it allows you to kind of follow the plot of a novel, like a video novel. They actually deliberately excluded Project Gutenberg, so even if it is, they probably do so well there. But you see like some story that is not out there, including anyone who can go into a movie, start learning the characters are, the relations between the characters are. Watson can't do that, wouldn't be able to handle duplication involving little notes. Intelligent creatures that often deal with novel cases they haven't encountered before, and not every answer is spelled out on the web. I think 85% of what's going on in AI today is vulnerable to this issue. So the answer is now moving internet. Current machine learning techniques tend to fail. I wrote one of my York pieces about this work by Hector Levesque, my colleague Rick Davis, and York. York for what they call Winograph schemas, in honor of Terry Winograph, as you guys know, Chisholm Ramaki was an advisor to Larry Page's very good thing. Just some pretty early AI work. So there's examples like this. Joan made sure to thank Susan for all the help she had given. We'll give it now. If you're a human being, you can answer a question like this. You figure out, based on your knowledge about words like help and what you might mean, you can figure out who's doing the help. Another example is the large ball crash. Let's put the table because it was made of styrofoam. What was made of styrofoam? The large ball for the table. People can do these things, but if they're not Googleable, if you're giving examples in and out there on the web, most machines are lost. Let me do the last part of the talk. I think the pretty negative. The first part is we give talking about how I think we might do better based on things that I've noticed basically as a cognitive scientist for the last couple of years. The first thing I'm going to do is, Kid Zero is not everything given to do easy copies. So I don't want to say anything that people do is something that you get into AI, because some of the things that people do are probably not actually that great. Like my short-term memories, I was not even 7. We don't even have 7 plus or minus 2 buffers. There's about 4 plus or minus 2 buffers. Nobody would want to say hey, I don't think it would be a good idea to go building AI systems that have short-term memory buffers that were limited to storing 4 pieces of information. I think that would be tying my hands behind the back, so I need to go there. Our long-term memory systems, I think they stink. You put information in, but you have no way of getting it out. Google obviously has a much better handle on how to have massive databases in which you can retrieve the information. I think we would be better off looking at systems where they're massive apps and people did that than trying to borrow from people like our long-term memory. Obviously, you don't want to borrow our mathematical precision, which is still, and so forth. So our egos interfere with our capacity to reason. We often short-term considerations overrun long-term plans. I wrote about a lot of these things. Michael Clusian commented about them in his book. So we don't want to just take more really anything that people do, because some of the things we do, we're not today. But I'll now give 8 or 9 suggestions for things that I think people do well that we would be advised to look at in terms of AI. The first is I think we have an app brain. In the limit, you could argue that intelligence equals knowledge plus inference. I'm alluding to the classic textbook, I guess textbook, but I think it was called Programs Equal Algorithms plus Data Structures. I think you can argue intelligence is having a knowledge plus inferential techniques. The knowledge part of things is getting cheaper and cheaper. Big data basically is knowledge. It's become plentiful. We have things like GPT that encapsulate machine-driven form things that would take human beings decades to learn like ever. Like I already said, even Watson is good on the knowledge side, but not on the inference side. Therefore, I suggest that going getting back to the human literature, and I think improving on it, might be pretty useful. Look, having a serious look from the perspective of AI, and why is it that humans are better at taking inferences, I think might be a profitable direction. The second is, and there's some overlap with these, right? Ideas, I don't think the 96 ideas that you relate to those. Humans come well with and have high tolerance for inconsistency. So we all know that average sight equals average fine, and we also all know that average takes hard for pondering. If you want a classical logical system, you know those two things, you are done, right? A classical logical system, from a contradiction, you can derive anything. So once you allow these two into your system, you can infer that the moon is made of green cheese. You don't want a logical system that concludes that because one contradiction happens to be there. Human beings have ways of coping with contradictions. I think that there's been a bias, not 100% bias, but a bias in the AI literature for looking for systems that achieve to demand a higher level of consistency that humans seem to do. And I think that that's a comfortable area for exploration. We also have an knack for knowing what differential principles are relative to the human domain. So we know, for example, if we're thinking about a human being as a physical entity or a psychological entity, usually we think about human beings as psychological entities, and when we want to manipulate other human beings, we think about what their psychology is and what we take them and want to do this thing about them. Occasionally, this is an example from Steve Pinker, we think about physical objects like there's a character in a TV show, Elliot Ross, pushed down an elevator shaft. The psychology at that moment seems to be relative to the character in his life, and as he went down the elevator shaft, he started to think about the physical principles. So we have different micro-theories, if you use the word occasionally used in the AI literature. We're really good about knowing which ones are relevant in particular information. You think of this as kind of a gating problem of knowing which set of knowledge to use at particular times. I don't think there's ever been any really good cognitive science studies of how people do this. There are some really old studies that how people can do this, but nobody has really systematically studied it. I think it would be really useful for AI to have one of them. Number 4, generics. The generic is in a sense like dogs have 4 legs, which to use AI terms is feasible. It doesn't have to be 100% true. And you can compare that to universally quantified logical statements like, well, X says X is a dog, dog has 4 legs, X has 4 legs. Generics are not the same thing as first order predicate calculus modifiers. We're really good at most machine logic systems and start with first order predicate calculus, and then people have debates about should I have second order, third order, and so forth. But our soul, what humans do, or what we teach our kids, and so forth, is generic. Many of those are just physical truths. And if it was just that, I think we'd have problems in AI, but it gets worse. So you say cars have radios, most cars have radios. Maybe there used to be in New York that a certain percentage of cars no longer have the radios. That seems to have stopped substantially on the error. But there are some other kinds of generics that I think are not as easily captured in AI, and I think AI should look harder at these things, kind of thing. One example is Duck's weight edit. This is not actually a statistical truth, in the sense that it's not true with the majority of ducks. There's a simple proof of that. I haven't actually gone out and tabulated ducks and egg laying, but I know that 50% of ducks are male, they don't lay eggs, and I know that some ducks are either not folded off or too old, and so forth, so they just lay eggs. So my back of the envelope calculation is maybe 30% of ducks lay eggs. And yet we still think that there's a truth to it. Maybe, I should go over the true and close to it on the slide. But there's a way we can understand this, we can make useful inferences, even though it's statistically unknown. And there are even more common cases like mosquitoes carrying malaria, which can be quote true, even if most mosquitoes don't. So when I come to mosquitoes go to malaria, you should get a shot. Kids getting malaria, you should get a shot. You don't sit there worrying about, well, is it true that 98% of mosquitoes or 2% of mosquitoes get the shot and you understand what I meant? We're not so good unless maybe people in this world, probably the people most likely in the world have a solution to this. But in general, I don't think machines are have really captured this. I know there's a lot of interest here in textbooks. Turns out even 4 and 5-year-old kids understand these errors. I think if you look at textbooks, you see a lot of them. More attention to how 4 and 5-year-olds can understand and reason about these errors is worthwhile. Humans really care about causal principles. The easiest thing to get out of big data is correlation. So you can write a very simple music recommender system. It's very well correlated. People that like Dylan tend to like the Beatles. If they know one, people tend to like the other. So there's obviously more studies that he made from big data and correlation. Then he has data sets that try to have a causal relation. But I think cause is represented in the data in the very thin range. It's kind of like there's a number on the likelihood of the cause. There's like a probability of B given A. And I don't think this is how human beings think about cause. So again, thinking about kids or scientists, people are constantly searching for explanatory principles. We don't want to just know that X causes Y. We want to know why. Sometimes we settle for not very good explanations, but we're always looking for the scientific ways to go around these. When you can't ask you why is the sky blue, they're not asking you what is the conditional probability that the sky will be blue. Given this or that, they want to know what makes it so. They may try to open up their understanding. But this is what I think people are trying to do. So the word of the day, thinking about Jeopardy and Daily Double, the word of the day is apophenia, which is a kind of like pathological case of human beings search for causal principles. Now, apophenia is the experience of seeing primary connections in random or meaningless data. For example, you have people that will look at sequences of lottery numbers trying to find the pattern, trying to find the causal principle. That's when the system, I think, goes too extreme. But we have a kind of way that can go to that length that is looking for causal patterns. And I think better is that part of what's going on. We also have a knack for approximation and shortcuts. Generics are one example, but there are lots of others. For example, three-dimensional physical reasoning problems that you might solve by using a theory relation to every molecule in perfect detail, we often solve, I think, by having a kind of one-dimensional or two-dimensional representation that your cartoon or caricature or sketch of what's going on rather than trying to model every detail. So for apple coffee spills, you see it start, if I start to spill this water, you can guess that Warren is at risk, he's not looking this way, and Peter is not, without having to calculate every molecule of my arm, what's in there, and so forth. So we often trade off reliability for speed. You have slightly less reliability to get iterate fast and get good results. And I don't think there's any real cognitive science literature on how humans do this, but I think if there were, it might actually be more with yes. So the bigger point is that humans are comfortable reasoning with complete information. So if I tell you I have a sealed box, in which I have inserted the spider before I seal the box, and I shake the box, and ask you, will the spider come out? You can just tell me no. Whereas you can imagine a computer saying, well, can you specify the size of the spider, how big is the box, how many times did you shake it, and what velocity, what algorithm governs the spider's motor control system, and so forth, in order to give you a meaningful simulation of what's going on. We've got, Ernie Davis and I working on this particular problem, trying to figure out essentially a logic system approach, although they call it a hybrid approach, trying to understand how people reason about containers, which is a recurrent theme in a lot of things that we analyze, not just containers themselves, but for example, in biology, we think about exponential containers. Even provide many different learning algorithms and not just one. So there's always this thought for a single learning algorithm, but if you look at human beings, we do things like association and correlation detection, which are close to the things that are popular in machine learning. We also do things like observational learning that are not very well captured. I watch you do this and I try to do the same thing. I see you swing a baseball bat and I try to do the same motion. We have implicit instructions. So I tell you, here's how you play Monopoly, this is what you're going to do. Right? Nobody learns Monopoly by digesting the recordings of 2,000 games of Monopoly and guessing what might happen next. We have specific systems that try to calibrate particular information.
Con benci già parlo, direi.